Raw, uncontrolled electrical faults can tear through industrial factories and instantly fry delicate microelectronics. And when a sudden, high-voltage spark arcs across a system, the resulting heat and energy are utterly destructive. Human reflexes are simply too slow to stop this level of damage. By the time you spot a surge and reach for a switch, the equipment is already ruined. Or worse, a fire has started. To safely harness electrical power, we rely on an automated electromechanical baseline, and that process starts with power conversion. This diagram illustrates a switched-mode power supply, or SMPS. Notice how the chaotic, alternating AC sine wave enters the central switching transistor block and outputs as a perfectly flat, regulated direct current. By using high-frequency switching to rapidly turn transistors on and off, the SMPS converts this power highly efficiently, minimizing energy lost as heat. Efficient power regulation is the mandatory first step in any control panel. You cannot safely protect or distribute energy until you have stabilized it. Once the power flows in a stable current, the system needs physical gates to safely route that energy and turn circuits on and off. The primary device for low-power signaling and simple switching tasks is the electromagnetic relay. Here, we see the internal mechanics of a relay. When voltage is applied to the central coil, it generates a magnetic field. This field physically pulls the metal contact arm across the open gap, snapping it into a closed position to complete the circuit. For high-power applications, we scale up to a contactor. This heavy-duty equivalent uses the exact same magnetic principle, but is built with robust contacts and enclosures to handle thousands of amperes for heavy motors, industrial lighting arrays, and massive heating units. Relays and contactors operate as the mechanical muscles of our electrical systems, blindly executing every control command they receive. But we have to ask, how does the system react when a command is wrong or a violent external surge hits the line? The most immediate threats to heavy machinery are sudden peak voltages and massive short circuits rushing in from the grid. Our first line of defense is the miniature circuit breaker, or MCB. It trips to instantly cut power during a rapid surge. Unlike a traditional single-use fuse that burns out and needs replacing, an MCB is completely reusable with the simple flip of a switch. When managing massive industrial faults reaching up to 2,500 amps, engineers step up to the molded case circuit breaker, or MCCB, for heavy-duty overload and short-circuit protection. These breakers do not trip at random. Their logic is dictated by precisely engineered parameters called trip curves, which measure the fault against multiples of the system's normal rated current. This graph plots multiples of rated current against trip time to map out those parameters. On the far left, highly sensitive breakers, classes Z and A, drop sharply. They trip instantaneously when the current reaches just 2 to 3 times the rated limit. Moving to the right, we see the curves for classes B, C, and K. These expand the tripping envelope, allowing the breaker to tolerate moderate, expected surges between 3 and 12 times the normal operating current before cutting the power. Finally, the Class D curve appears on the right edge. This class is highly tolerant, ignoring temporary spikes, and only tripping when the current skyrockets to 10 to 20 times the rated limit. This is necessary for massive industrial motors that require huge amounts of energy just to start up. By selecting the correct trip curve, engineers tune a breaker to ignore normal operational spikes, while instantly stopping catastrophic, factory-level surges. While breakers protect the hardware, human bodies require a distinct, far more sensitive type of protection. We need a way to stop invisible electrical leakage before it causes a lethal shock. That is the job of the Earth Leakage Circuit Breaker, or ELCB. Its core function is to continuously monitor systems strictly on a voltage basis, hunting for any errant electricity escaping to the ground. Because a few milliamps can stop a human heart, the ELCB operates with extreme hypersensitivity. It is designed to trip at minuscule leakage levels, ranging from just 10 to 500 milliamps. ELCBs cover a wide operational spectrum. A Type AC breaker handles simple sinusoidal AC leakage, while higher-end models, up to Type B, protect against complex high-frequency currents and smooth DC leaks. The ELCB acts as the ultimate fail-safe for human life, transforming what could be a lethal shock into a harmless, instantaneous mechanical click. Not all electrical hazards result in instantaneous explosions. Some are a gradual, quiet threat, like prolonged thermal overload building up inside heavy industrial motors. To defend against this slow, heat-based destruction, we install an overload relay, or OLR. Inside an OLR is a bimetallic strip made of two distinct layers of metal. As excess current flows through it, the strip heats up. Because the bottom layer expands faster than the top under heat, the entire strip physically curves upward until it snaps the circuit connection apart, cutting the power. The Motor Protection Circuit Breaker, or MPCB, is the all-in-one evolution of this technology. It combines that thermal overload defense with short circuit and phase failure protection in a single unit. To accommodate different equipment, MPCBs use specific trip classes. These enforce a strict time limit, ranging from 5 to 30 seconds, giving a heavy motor just enough time to safely start before the device cuts the power. These specialized motor protection devices prevent the invisible, gradual buildup of heat from quietly destroying the most expensive and vital mechanical hardware in a facility. When viewing a complete electrical control panel, we should see it as a unified, automated safety ecosystem, rather than a collection of individual parts. In this complete circuit diagram, you see how perfectly these components harmonize. The SMPS regulates energy, contactors direct traffic, MCBs shield from surges, ELCBs protect human life, and MPCBs guard the motors at the end of the line. I encourage you to review the specific trip curves and thermal logic discussed today so you can design and maintain safer systems. If you found this breakdown helpful, subscribe for more deep dives into complex engineering mechanics. Engineering mastery requires orchestrating the exact, precise mechanical logic of how and when to shut a system down, a challenge even greater than powering it up.